this talk is about static binary injection, and in the talk we introduce our new tool named Redback, which is an advanced tool for static binary injection. Okay, so this work has been done by a team of 2 people, my co-speaker and me. And my name is Nguyễn Anh Quỳnh. I'm working in Nanyang Technological University of Singapore. And in the last few years, my research focused mostly on binary analysis. And I'm the founder and the maintainer of a few open source reversing frameworks like Capstone Disassembler, Unicorn Emulator, and Keystone Assembler. Okay, my co-speaker is Đỗ Minh Tuấn, and he's a researcher at SciStack. He is interested in fuzzing and exploits. Tuấn is a member of Baby PhD CTF team, and he gave many talks at XCon, T2, Black Hat USA, and Black Hat Asia. So in this talk, we first introduce briefly the background on static binary injection, and after that we show how we develop a new tool named Redback, and we present the methodology of Redback and the implementation, so you can see how Redback supports different file formats like Mac-O, ELF, and Windows PE files. We have some demos in our talk, and finally we have conclusion. Okay, let's talk about static binary injection. Static binary injection is a technique to physically patch external binary into executable file. So at the beginning, we have an original executable file and some external binary. We inject the external binary into the original executable file, and as the output, we have the new output executable file, which include all the original executable and also injected binary. So you can see that the output, the size of the output file is bigger than the original executable file. There are two main cap binaries to inject. The first one, very simple, is shellcode. So we can inject shellcode into executable file, and you can see that because shellcode is very simple, it's very easy to develop a tool to inject shellcode into the executable file. But on the other hand, you can see that because shellcode is mainly written in low-level assembly language, so it's very expensive to develop and maintain complicated shellcode. So this second type binary to inject is totally different. We call that high-level binary. So we have some source code written in high-level language like C or C++, and we build them, and as the output we have high-level binary. And static binary injection can inject this kind of high-level binary into the executable file, and you can see that on one hand, it's easy to build, to maintain this kind of binary because it has source code. But on the other hand, this kind of binary is very complicated, so it's much harder to build injection tool for that. And this talk is mainly about how to build an advanced tool to inject high-level binary into executable file. So there are many good reasons why you want static binary injection. So we can inject code into one program to add new features, or you can inject code into the program to observe the target behavior at runtime. And static binary injection has many applications. First one is persistent infection, because this is what all the malware want to do. Executable packer or protector also need to inject and modify the program. And finally, static binary instrumentation also want to physically patch the program to change to inject the code into the program. Static binary injection has many advantages. First one, it offers much better performance compared to dynamic binary instrumentation. You can easily instrument early system code like firmware, bootloader, OS kernel, and also static binary injection give you much better control on the location where you inject the code into the program. And finally, in some special cases like embedded system, static binary injection is the only solution. Okay, looking at some existing tools, you can see that most tools nowadays, they can only inject simple shellcode, but not high-level binary. They only work on some limited platforms, and they also limited on the file formats they can support. So we think that we need a new, better tool for static binary injection that can inject high-level binary files built from C or C++. This tool should work on on-cap OS like Windows, Mac OS, Linux, and so on. And finally, it should support on-cap popular executable formats like Windows PE, MacO, and ELF. So the result of this research is a tool named Redback, which is an advanced tool for static binary injection. Redback can inject high-level object files built from C, C++ into executable file. That means you can inject Windows DLL into exe files. You can inject dilib files into MacO executable. You can also inject .so files into ELF executable. Redback run on all popular OS like Windows, Mac OS, Linux, BSD, and Redback support all the popular file formats like PE, MacO, and ELF. So how we did it? So the general idea is when we inject code into the executable file, we leave the code and data section of the original file in the same place. We do not move code or data around. To contain the new object binary in the patch file, we expand the original executable file by adding some new sections. And after that, we copy the content from the object file to the new sections. And because the object binary built from C, C++ is mainly for dynamic linker, but not ready for execution, so the new content injected into the output file need to be relocated so they can run properly in the new place. So Redback has two main challenges. The first challenge is to add new sections, because we need to append new sections, but this activity can break well-structured executable format file. So we need to be sure to have a correct to correct all the section element and size after injection. And after that, we need to fix metadata output executable file to make the whole file legal, so we can run properly on the system. So in these steps, you need to fix many things in the file headers, like size, the total size, the new number of sections, the new checksum. And sometimes we might need to even to create a new file headers and new section headers to keep the new content. The second challenge is relocation. So remember that we patch the object binary into the target binary. So we need to relocate the object binary in the new place. So just few ideas we follow. We need to keep the distance between the code and data section in the object binary intact, so because they can still refer each other. And basically, Redback need to develop a special type static linker to link the injected object file with the existing executable binary in the original files. And Redback need to change the metadata of the object binary in the new place. So the system dynamic linker is aware of the new injected content. And finally, we need to avoid patching any code or data, but only modify the file metadata, like import function, relocation, and so on. Okay, so now my co-speaker will take over and he'll show you how Redback can support Mac.o file format.
Hi, I'm Tuấn. So now I want to show how I static inject into Mac.o file and ELF file format. First, let's take a look at the Mac.o file format. This kind of file has a header which includes magic number, CPU type, sub-CPU type, number of block comments, and total size of block comment. The flags in header also bring some special bit like mhpi and mh no heap no execution. Then load comment, padding zone, and data come. Load comment is a type of header that contains information of segments like text, data, etc. Among all the segments, LC segment is noticeable that it guides the loader to load binary onto memory based on file size, file offset, VM size, VM address, initial protection, and max protection. Talking about the challenge when I add new segments or sections, I create two new segments, RB text and RB data, by putting segments header on padding zone and fix some numbers. Then I clone all the desired sections header, append them to these segments, and place their content at the end of the file. However, this can only work for macOS, Mojave, or older versions. So you can see here is a new binary format. Next challenge I have to face is relocation. I choose to inject a dynamic library to target binary because every object inside the library has been relocated. However, global pointers are still offset, not addresses, and index of libsystem.dylib in library may be different from the target binary. Opcodes and stuff need to be fixed also. So I take the advantage of dynamic linker to handle new contents. The dynamic linker is defined in load die linker load command, and there are two types of symbols, lazy and non-lazy symbol pointer. Beside a die syntab, dy syntab load command store information about offset, size, and some kind of numbers. This example here called the putS function. At the beginning, the putS is not located inside the binary, and it will be bound when the first call is made. Instead, putS holds a pointer point to stub section. That stub call directly KYLD to find the address to a relevant function. Then it overrides on original pointer. You can see the illustration here. Other segments we need to pay attention are link edit and DYLD info only. The link edit holds opcode and some other information. Meanwhile, DYLD info only contains rebase and binding information. Opcode actually is a single byte and encoded by unsigned ULEP 128. The byte opcode is used to look up external function, and the rebase opcode is used to deal with ASLR. For example, this image shows how a sequence of rebase of code should run. Firstly, it sets the type to 1 as a pointer type. Then set the current segment index to put as pointer on non-lazy symbol pointer section. And finally, it performs the rebase one time. The same as for binding opcode, it finds the location of press, set the index of lib system, restring as name of symbol, and then bind and write the result to the location. So now I have enough abilities to control the DYLD to do what I want. For pointer relocation, I clone the original rebase opcode to the end of link edit segment. Then append the libs opcode. I also need to fix some information on segments header. And I not only do the same for binding opcode, but also fix lib systems index and stack index when pushing arguments. Here is the new link edit layout. And here is a sample code to demonstration. On the left hand side is the target binary, and on the right hand side is dynamic library. And now I will inject library to this binary. First, I pass the library to my tool. My second argument is the original binary. Then this is the output. After I run, you can see the change in size of both binary. Meanwhile, the new one still remain all the feature of the old one. Next, I would like to discuss about ELF file. The format has some headers, symbol table, and dynamic symbol table. In ELF file, segments are also used to map from file to virtual address space. There are some sections such as .text, .data, etc. And in order to add new segment, I try to append new data to segments data, then fix metadata on segments header or add new segments header if necessary. However, there is not enough space of padding to insert new header. Furthermore, some sections are dependent on other sections. For example, there are many pointers which point to .text section are stored in symbol and dynamic symbol table. Therefore, to make it right, I create a kind of graph of dependencies that if I change the value of the node, its neighbors will automatically its neighbor will automatically be updated. So the new layout looks like this. Regarding about relocation, it is simple to patch the internal data like relative or global data to be fixed with new segment. Then I leverage the dynamic linker to import new function. The dynamic linker is defined in a .interp section. It sets up environments based on information of .dynamic sections. The linker uses a method called lazy linking to resolve function reference with support from .got and .plt sections. The program here called putAdd function, which point to .got entry of putAdd to its .plt at load time. After the putAdd call is made at the first time, the .plt gets control, resolve symbol, and then linker will update the .got entry to hold the final value to be used for future calls. This is how an entry in dynamic symbol table looks like. It uses the index of symbol on the table dot relative PLT to pass to the DL runtime resolve function. The solution now is quite easy. We just add new entry to some sections and then add new set string and add new string of that symbol name to string table. Of course, we have to patch some value and fix some indexes also. However, because we modify offset of sections, so the binary should be a PIE type to remain the structure. Here's my demonstration for ELF file format. Like what I have done with much of file, I pass the library and the original file to my tool. Then I run my tool, checking size, run the original one, and run the final one. Next, Mr. Quinn will continue our presentation.
Okay, so now let's see how Redback can inject into the Windows program. So Windows program has a format named PE, and we have PE format for 32-bit binary. We have PE plus for 64-bit binary, and we have two main cap executable binary in Windows. The first one is DRL, which is for dynamic library, and the DRL, one DRL can depend on many other DRLs. The second very important cap binary is exe files, which is for program, and one exe file can depend on many other DRL files. So the target of Redback is we want to inject DRL files into the exe files. So as output, we have a new output exe files that includes the original exe files and also injected DRL files. Okay, so Windows has its own dynamic loader and linker, and we must understand very well how the loader and linker in Windows work, so we can make Redback to be compatible with all the process, so the output binary can be properly run on Windows system. So P file format is actually very complicated, and we do not have enough time here, so I just mentioned some important points. So P files has a header named empty header, which tell you more about other headers like file headers and optional headers. File headers has some important information like the number of sections and the types of optional headers, so we can locate where the optional header stays in the memory and on the disk. After the file header is the optional header, and this header has many important information like the entry point, the base of the files in the memory, section alignment, file alignment, the size of the image files in the memory, the checksum, and there's one important structure named data directory, which is a very important structure because it points to many important metadata of PE file. And data directory actually contain many other directory. So we have directory for export function, we have directory for import function, we have directory for relocation table, we have directory for import arrest table, and so on. So one PE file can have many sections, and each section have one section header, and each section header point you to the location of the section in the memory, the size, and we have some very important entries in the directory entries. One is import entry, which tell you how to which tells the system loader and linker how to locate the DLLs that this program depend on and which function the program need to load on into the memory to make the program run properly. So we have import descriptor, we have tank data, which tell us where to locate the imported function from which DLL on disk and in the memory. So we see that Redback need to add a new section for the injection. So to create a new section, we append a new section at the end of the original program. And after that, we need to align them so they can be recognized by the system. So the size of the section need to fit the injected object files. So we need to adjust the virtual size, the size of the rotator, and we need to align the section as well in the memory. And actually, we need to append not only one but probably many sections, like section for program, for code, for data, for read-only data, for imported data, and for relocation. So after we append the new section, we need to fix the P headers. So we need to fix the size of total headers. We need to fix the size of total image. We need to fix the size total code in the program. And finally, we need to pump up the number of sections. So after we add the new section, we copy the object binary from the DLL files into the new sections. And there's one important thing to do. We need to relocate them. So each XJ file has one relocation section named reloc. And also the object files, DLLs, also have its own reloc sections. However, as the output program, Windows only recognize only one relocation section. So we have to do some tricks here. So we append a new big section for relocation, and after that we copy the .reloc section of the target of the original program, and also the .reloc section of the DLL files there. And after that, you need to relocate them. And finally, you need to fix the entry in the data directory for this new relocation section. And besides the relocation section, we have to repeat the same process for important table. So because one XJ file only allow one import directory, so we also need to append a new big section for import tables. So we do the same thing, very similar. Okay, so one thing you need to pay attention is that because the code in the code coming from the DLL files need to be executed at runtime, and the code there can refer to the other imported function or variables. So we need to have some relocation for imported function as well. So to do this, we need to add new entries for imported function in the injected object files. And Redback actually append a new data section for imported function. And after that, it copies the imported entry from the target program. And also we need to copy the imported entry from the object files onto the new entries in the new imported sections. And finally, Redback need to fix import a rest table of the injected entries so the final program can run properly. So we have the very short demo for Redback, so you can see how Redback can inject DLL files into the XJ files. So in this demo, we have a very simple program named Hello World, and you can see here this Hello World does nothing but just print Hello World to the console. And we have another source code for DLL files, and this DLL files actually also very simple. It does nothing but print injected to the monitor, and it exits. So we want to inject this inject true files into the hello world file. So we build the hello world file and the injected true files into some binaries, and you can see here. So we build the hello world.c, and we have the hello world 64.exe files. And we build inject true.c to inject true 60.dll. Now we want to inject this inject true 60.dll into inject 62.exe. So first I can run the hello world so you can see what it does. So the hello world 60.exe files does nothing but just print out hello world to the monitor. And now I run Redback. So my tool will take one input, which is the DLL files, as the first argument. And after that, the second argument is the name of the exe files that we want to inject into. And the final argument of Redback is the name of the output file, which is hello world minus rb.exe. So I run this command. Yeah, you can see that Redback takes the inject 62.dll and inject the .text section, .data section, .data section, .idata section into hello world 64.exe, and as the output it generates the new exe files named hello world 64 minus rp.exe. And now let's try to run this new patch file. So you can see that you have the new file here, and this one is already has an injected DLL file inside. So let me run this hello world 60 minus rb.exe. So you see that now the injected files, the patch file, just print out injected as output and exit, which is totally different from the original file here. Okay, that's it, and here come my conclusion. Redback is an advanced tool for static binary injection. It can inject high-level binaries, object files, built from high-level language like C or C++, and it works on many OS like Windows, Mac OS, Linux, BSD, and it supports multiple executable formats like Windows P, Mac OS, or EF. And we are going to release Redback with the full source code to the internet, to the public after our talk, and you can check our website growx.io/Redback for release announcement. Thank you. And now come the question and answer session.